Hello everyone, I am Nimisha Tripathi, a senior lecturer in the University of Greenwich, and I'm going to present a joint work which was undertaken by myself and Professor Colin Hills on low carbon options for biomass waste valorization. Before I start my talk, I would like to share this picture with you all. This was presented in COP26 when we represented Universities UK, and this picture shows the summary of actually what we are doing in the lab at Greenwich. And in this picture, you can see a cylinder of carbon dioxide, which is pure carbon dioxide gas cylinder, and you can see some aggregates. So the work what we are doing, we are using accelerated carbonation technology to valorize waste, solid industrial solid waste, and making construction materials, including aggregates and blocks like this, you can see. And this work goes back several years now, and now it is commercial already over last decade. But what is new to this work, what is the new development, is the picture you can see here. This is the biomass waste which has been used or valorized to make materials which are fit for purpose in construction. And this is the work what I am leading here or I am involved with. So I'm going to talk about this part, which is biomass waste. So the talk today will include background, a bit of background of the work, the biomass, including current biomass waste issues, global allocation and flow of wood biomass. I will talk a bit about biomass waste management scenario and a special reference to emission scenario and sustainability credentials. Biomass waste as a resource will be included in today's talk. And I will also talk about opportunities where we can combine biomass with carbon dioxide to add value or valorize biomass waste. And this will be supported by a case study which was undertaken at Greenwich. And finally, I will conclude my talk. So when I'm talking about biomass waste here, basically I'm going to discuss the plant-based biomass waste, and that includes these type of materials like nutshell and some fibrous materials, fibrous residues from sugarcane, for example, and fruit peel, fruit waste like banana peel and orange peels and so on, but not only limited to agricultural or cereal crops or residues generated from those. I am going to talk or touch upon a bit about wood biomass waste as well. So a bit of background. So why target biomass? Biomass is ubiquitous, biomass waste is ubiquitous, and biomass is grossly underused as a resource, and there is a growing opportunity because the supply of energy is growing as we are moving towards renewables, and as the world's population grows, we are going to produce more energy, we need more energy intensification, and we have to think about alternative fuels. Agricultural activities are being intensified and increasing waste or residue generation from harvestable and non-harvestable biomass is projected, and biomass residue generation from crop yield is inevitable. So with respect to biomass waste, current global biomass waste, including animal waste here, uh, the data show that about 140 gigatons of per year of biomass waste is being generated. Globally, about 66% of the residual plant biomass comes from cereal straw only, with over 60% being produced in low-income countries. But also in Europe, straw residue production is quite significant, and the literature data show that about 340 megatons or million tons of straw residue is produced in Europe. And cereal and oil crop residues which are generated in Europe are in the range of about 416 megatons. Not only agricultural and cereal crops residues are available, but also global wood-derived biomass residues are about in the range of 4.6 gigatons. And of this all, about 60% goes to energy, 20% to wood industry, and remaining is left to rot. And that is available to be used, or that needs management options. So I will talk about that a bit more in detail in a few minutes. Now, looking at this figure, projected global demand for cereal crops, from some literature, I have taken these data and including FAO data. And this one shows over from 2008 to 2050, or that projection, if we see, about 1 billion tons of increase in biomass waste has been projected over this period, and this is anticipated to be partly met by growth in the developing countries, as you can see these bars here. So this much projection in crop yield has been anticipated or projected, and this involves residue generation as well. So what is the current biomass waste issue? Globally, about 517 megatons of unexploited cereal crop residues are available. More than 2 gigatons of crop residues are burned. 18% of global CO2 emissions come from these crop residue burning. In developed countries, biomass wastes are partially used for energy and also for heat production, whereas in developing countries, they are largely landfilled and used for household fuel or energy production. And this is really interesting to know that biomass energy has the fourth highest carbon footprint of all energy types. And the emissions are in the range of about 230 grams of carbon dioxide per kilowatt hour energy produced. So biomass energy in true sense is not that negative carbon is involved, that has high carbon footprint itself. Incineration or pyrolysis generates substantial amount of ash as coal is being phased out with some capacity being converted to biomass. Drax, which is the biggest biomass energy producer or incinerator in the UK, produces about 1 megaton of fuel ash and about 0.24 megatons of furnace bottom ash. So these ashes need to be managed. And then there is footprint associated with this, because for disposal of ashes or management of these ashes, transport, for example, is required. The another issue is use of pellets. Increasing demand for wood pellets is another aspect that needs consideration. The EU consumed about 18.3 megatons of pellets, or 79% of global consumption on its own, for energy production. The global use of pellets is projected to increase from 22 to 50 to 80 megatons by 2020. It was projection few years ago, and that this one is going up again because new data shows further increase in pellet use. So pellet demand is quite increasing in Europe, especially. A significant potential of wood-derived biomass is currently going to waste, being directly detrimental to ecosystems. So biomass waste can be used as a resource, but at the moment, large proportion of this is going to be in landfills or being burnt, as I said earlier. So about 55% of global wood harvest is estimated to be burnt as fuel. 70% of this is left to decay in immediate surroundings of its original production, and most of the biomass ashes are disposed of in landfills. The remaining 45% is used as industrial raw material as per UNEP report, which is quite old report, but this gives a bit of understanding about what residues available that can be managed or used. So based on some literature, we had calculated how much waste, how much wood biomass is available and how the allocation has been done. So about 4,600 megatons of wood biomass available. About 1,300 megatons goes for fuel purposes, and that is used for biomass energy production, and about 923 megatons is lost, whereas about 923 megatons from 4,600 megatons goes for industrial roundwood or uh, or pellet production, and rest 923 megatons is primarily left to rot or is lost as primary residues. This slide shows the pellet production projections for selected regions, and we can see that demand of pellets is quite increasing significantly. In countries like China, we can see a significant increase here. North America and South America are not behind, and Europe is also increasing its pellet demand. And in terms of monetary terms or economic terms, the global wood pellet market estimates show from 2019 to 2025, there is an increase projected from 10.5 billion US dollars to 24 billion dollars US dollars. So there is a projected increase in pellet market throughout the world, and the energy production definitely is not a clean process here as well, because as I mentioned earlier, ash production and other carbon footprints are inevitable. So if we look into biomass waste management options now, there are options where we can utilize biomass waste, and this utilization approach already is in practice, which includes open burning in field and household fuel, for example, but these have high carbon footprint, and the process is quite carbon positive because of a lot of carbon dioxide emissions. But there are some valorization approaches as well where we can add value to these biomass wastes. But some of these valorization approaches also are not that carbon negative as they should be, or they are seen as, because gasification, for example, or biofuel production, for example, they have CO2 emissions involved, or high temperature requirement for gasification, for example, which has carbon footprints associated. Our approach is we try to think about valorizing biomass waste using accelerated carbonation approach, and this approach looks much promising because CO2 emission is negated in this process, and we apply CCU or carbon capture and utilization approach, and the material is given value which has use in construction, or which has potential to be used in or applied in construction industry, and the carbon footprint associated with the process is much lower than other valorization processes. So the product what we make is quite carbon negative. So when we are talking about emissions and using biomass waste for biomass energy production, I'm really concerned about emission scenario because the possible longer term impacts of repercussions of biomass to energy conversion are quite obvious, because one way we are diverting our biomass from landfilling by using them for biomass energy production, but ash generation and transport requirement for disposal of ash and CO2 emission associated with biomass to energy conversion, or burning of biomass in incinerators, is further having carbon footprints associated. So in one way, we are diverting biomass from landfill and we are producing high carbon electricity in true sense. So where is the offset? Offset with a warming effect in true sense. And a few statistics we can go through. Biomass to energy emits about 150% of the carbon dioxide of coal and 300 to 400% the CO2 of natural gas per unit energy produced, as per literature. Carbon offsetting triggers the development of further high carbon infrastructure, for example, uh, management of ash, for example. So in that respect, there is no point in reducing emissions by 1 ton if the longer term knock on impact is 2.5 tons or even 1.2 tons. So where is the offset in true sense? For an offset activity to be genuinely low carbon, it must guarantee that it does not stimulate further emissions over the subsequent century. That means we have to think about direct and indirect offsets as well, to sum it up and bring it to low carbon or carbon negative. What are the sustainability credentials that we are talking about? Globally, carbon efficient management options must conserve the energy, minimize the carbon dioxide emissions at the uh, same time, capture and utilize waste carbon dioxide. So not only conserving the energy and reducing the emissions or minimizing this, but also we have to think about how we can make maximum use of the carbon dioxide, how we can apply CCU approach in our process so as to achieve or attain sustainability credentials. Valorize waste, so not only using CCU approach, but also valorizing waste so as to reduce the reliance on natural materials. That can help to meet the need of circular economy and replace carbon intensive products. For example, if we can replace SEM1, which has high carbon footprint associated, and if I'm not mistaken, it's about in the range of 760 kilograms carbon dioxide associated with per ton of cement production. So if we can replace some of the carbon or low carbon products with these carbon intensive products, then we have a win-win situation and we can attain or achieve sustainability goals. So what here is a small case study. What we did, we thought to use biomass waste as a resource, and we found that biomass wastes are having potential for being used as a valuable material that can be developed or converted into new construction materials. Our proof of concept study undertaken at Greenwich shows that biomass wastes can be converted into useful products using waste carbon dioxide that works as a glue. And in total, this is via carbonate formation using accelerated carbonation approach. Our innovation is a circular economic option. And why I say this as an innovation, because we found really something exciting stuff while establishing this proof of concept, which I will talk in a minute. What are the opportunities when we combine biomass with carbon dioxide? Valorization of solid waste with waste carbon dioxide using CCU approach. This is not new. The technology is already commercially available via University of Greenwich and its spin-out company Carbonate Systems. And this is a UNEP GEO6 case study. But we gave a new approach to biomass waste, where biomass waste can combine with gaseous carbon dioxide to make low carbon products. Resource utilization was demonstrated in lab, and end of waste process potentially achievable using biomass waste similar to other industrial wastes. So we investigated a big range of biomass waste, and categories included fruit peels, fibers, nutshells, and wood chips. And you can see some pictures of these variety of biomass wastes here. And these wastes were sourced in India, UK, and Africa. We followed three-stage process, including thermal degradation that consisted of production of ash or incineration of biomass to produce ash characterization, then its exposure to carbon dioxide and calculating embodied carbon or CO2 uptake. Then the second step involved raw biomass characterization, where we not only used or converted biomass to produce ash, but also we tried to work on raw biomass, including the properties for evaluation like moisture, fiber elasticity or tensile strength, surface area, and carbon content. And finally, we worked on product manufacture and testing. And very interestingly, we found that most ashes were carbon dioxide reactive and some were made to self-cement. This was exciting because this gave us complete new insight about this work. And we started working on mineral components of ashes and tried several permutations, combinations to work on. So going forward, we did, moving ahead, we tried making some products and promising biomass waste, including wood chip, fruit peel, and nutshell and fiber and husk. We made some cylindrical monoliths using ash only. Means when I say ash only, means biomass ash only. And the ashes were also used to solidify raw biomass with and without SEM1. So we took SEM1 as a reference material, but also because we had noticed that our ashes were having self-cementing properties. So we harnessed that potential and we mixed some of the raw biomass materials to glue it with the help of ash only and mineralized with carbon dioxide. And we use SEM1 as well in some mixes to compare or use SEM1 as a reference. So suitability was explored as low density construction products. And these were the products what we made. You can see whole range of materials we developed using aggregates, using ash like aggregates. Some monolithic materials we made using raw biomass, and these were glued with ash, and some combinations, as I said, with SEM1 as well. And we also managed to make some of these type of monolithic materials, which were having ash only, cemented by ash only using raw biomass. And this was really encouraging because this gave us an understanding of self-cementing property and its behavior, and the ashes behavior of gluing the materials or raw biomass together. And in this step, we found that not all biomass ashes were suitable, because you can see some of these materials or monoliths are showing a bit of crack. So some biomass ashes were quite hygroscopic in nature and they didn't perform very well. But I have to say most of the ashes were quite CO2 reactive, and they acted as a cement, or they had a property to self-cement. So we were confident that solidification with CO2 was impactful in gluing the materials together based on raw biomass and biomass ash based materials. Greater compressive strength was achieved on combination with carbon dioxide uptake in raw biomass cylinders containing ash. Products were lightweight, typically about lower than 500 kilogram per meter cube. The products are the subject of further investigation, including thermal and hydric properties. So we are working on these properties to explore the potential of these materials for their robustness in these respects. And some of these monolithic cylinders have shown really great high significant amount of CO2 uptake, and some wood shavings and sawdust were remarkably uh, good in taking CO2. And you can see some wood shavings were having potential to imbibe about 41% of carbon dioxide. But most of these ashes, regardless they were wood ash or agricultural waste, they had potential to react with carbon dioxide because their mineralogy was correct to react with carbon dioxide. And most of the monoliths we have produced, they had strength after CO2 uptake or carbonation, which was in megapascal range. This graph shows a CO2 emission and carbon CO2 capture potential approach or aspect of our work with our materials. And we calculated that CO2 emitted and CO2 taken up by many of these ashes, what was quite in same range. However, the mass loss during thermal decomposition is much greater than that gain during the carbonation of the ash. But still, this was quite promising that amount of ash, that amount of emission, amount of CO2 that was emitted during incinerator or combustion was quite comparable to what was taken up by the ash when we put carbon dioxide back in the material. And some of these bars you can see, they are quite similar, quite in the range. So this was further quite promising result. And we also observed the similar trend in CO2 capture in ash cylinders as well on weight gain basis, as you can see here. For example, in case of poplar shaving, for example, this was quite encouraging. This graph shows CO2 balance density, strength, and carbon dioxide uptake, where we mixed our raw biomass with ash only and in various combinations of cement and ash as well. And we saw that in all cases, the material has shown carbon negativity. Even where we have included or replaced some of the cement material with ash, we found that materials were quite carbon negative. So it gave us a confidence that these ashes have potential to be used to replace, even if not fully replaced. Means I am not saying this is a magic bullet or black box thing, but we still can harness the potential of using these ashes to partially replace hydraulic cement. These are some microstructural development micrographs are here. One micrograph shows 3 distinct microstructures, including carbonate formation. And here we can see the interparticulate carbonate formation here, which solidifies the monolith in one of our monolithic materials. This microstructure shows relic plantae structures here, and these are enveloped by carbonated cement. So we have established this proof of concept, and this high level evaluation of biomass residue and the CO2 reactivity of their ashes where shows that we calculated that about global agricultural residue, what is available in megatons, about 2,900 megatons per year, for example. And if average ash content is about 5%, and assuming about 70% of ash is reactive, we can imbibe or embody about 10%, 10 million tons of carbon dioxide in this amount of ash, assuming 10% uptake in these ashes, whereas in some of our materials we have seen much higher CO2 uptake. And similar calculation was made based on the global wood biomass to energy as well, based on how much biomass residue is anticipated to go in biomass to energy. And we can sequester or capture or utilize about 19 megatons of CO2 in about 193 megatons of reactive ash, which is produced per year as per our calculation. So it is quite significant amount of carbon dioxide utilization in these materials or in these ashes, in biomass ashes. And this work had definitely attracted the audience and the reviewers' attention in international journals, and we were able to publish 3 papers in Nature group journals, which was quite encouraging for us. And in one of these publications, we had calculated what are the offset pathways. So this figure shows that if the material or biomass residue is being burnt or landfilled and ashes are, and this is seen as or used as a waste, or not used as a used for something constructive, then this acts as a CO2 source. And the environmental perspectives related to this are: material is fated to go in landfills, ashes are produced, and there are CO2 tax or disposal costs associated. Whereas if the biomass residues after burning, this is used as a resource, we have opportunities where it can use as a carbon dioxide sink, and direct and indirect offsets are achievable. Direct offsets via capturing carbon dioxide in ash, and indirect offsets are quite significant as well, because we can replace biomass ashes with cement in concrete, and also transport costs are negated as well. And my argument is, even if we can replace 1% of cement with these materials, then we will negate about, thinking about 760 grams of CO2 per kilogram of CO2 equivalent, how much CO2 we can negate. So the economic and environmental perspectives are there: savings on waste, landfill and ash disposal costs, avoidance of CO2 cost, value addition to waste, carbon capture utilization benefits, reduce pressure on natural resources, and new employment opportunities as well are not cannot be ruled out. So this work definitely was received very well. And another calculation for CO2 offset, which was published in another journal, Scientific Reports, in 2020, showed that if we calculate or if we consider direct and indirect offsets, about total offset about 0.134 gigatons of carbon dioxide is possible in about 0.675 gigatons of selected fruit and vegetable waste, where we have considered citrus, banana and potato peel only, and major crop residues about 5 gigatons. So in total about 5.675 gigatons of biomass waste, we can offset 0.134 gigatons of carbon dioxide. So this is quite potential significance can be harnessed there. and benefits can be harnessed here. And to finally conclude, demineralization of carbon dioxide gas in biomass-based monolithic composites is now proven. Biomass ashes can be solidified and can be used to replace cement in carbonated biomass-based construction materials. And there is a potential to offset carbon as well, as I said earlier. The utilization of biomass waste with mineralized carbon dioxide can close the process loop, provide the sustainable management routes for residues, impart values to waste, either to left to rot in the field, and if we can replace hydraulic cement to produce carbonated biomass-based construction materials, there is a significant potential to offset carbon. So that's it from here. I will say thank you to everyone. And if you have any questions, you are more than welcome to get back to me. Thank you very much.